Alright, hell yeah. So this is no trivial problem. This comes from Hibbler. This is statics. And so what we're going to do, because this one's kind of set up different, it's one of the first chapter problems where you're not just doing free body diagrams, summing the forces in particular directions, and making sure the sum of the forces equal to 0. Because what you'd want to do is just take a free body diagram of that pin, say that we have a 400-pound force going that way. It would be sweet just to hold it back with 400 pounds, but we can't do that. The only thing we can do is do things along these two members. So that's kind of the first thing. And yeah, we could, I mean, maybe this, and it's not obvious, you know, even for me, but this top member is going to be in tension, so we can hold it back like that. We introduce a downward force, so hey, we have to have a compressive member to actually kind of push up. And so both of these kind of have components that way. So both of these have to equal to 400. You know what I mean? If this one's negative, this one has to be 400 plus whatever this was, if that was a negative component. This one has to have a downward component that's equal to that upward component. So that's kind of the general gist. And that's kind of a easier take. But these are some of the harder problems in these first couple chapters, because they don't introduce this concept of free body diagrams. All they say is that here's your 400 pounds that we're putting on this, and what it actually says is like, hey, let's put a force in this direction, you know, somewhere in this direction, and a force somewhere in this direction that add to 400. So it's kind of the opposite. If you take a free body diagram of the pin, you're doing the opposite. You're saying I have a 400-pound force this way, and I'm going to hold this pin back by putting a tension force this way, but also an upward compressive force that way. And so that's what we have here. So again, 400 pounds this way. I'm going to hold that back with a tension force. This component's going to be 400. I mean, just in general, that would be the case. I mean, you'd be shooting for that, cool, but you're now having a downward component that you have to push back up with. So this has to be 200, but now you introduce this component, so then you have to balance it out. So now this one has to increase maybe to 450. If this is 50, cool. This is not helping. This is pulling back both this 400 and this 50, and then this downward component not helping is being resisted by this compression. You know, that's kind of the general gist. But this problem just says, hey, if we start at A, and it says if we have a component 500 pounds in this direction from A to C, that's basically what it's saying. And I think that's a harder thing to do, is just like, how do you go this way and then somehow get over here? And so, well, you go this way, and then you get to go along this. I mean, you don't just like jump up there and then go along this line, but you know what I mean. We go down this, and then parallel, we can go along there. So maybe if we go down here. And, you know, sometimes you can just do this. If this is 4, booyah, so I'm going to go 1, 2, 3, 4, 5. I'm going to come down this way 5, and if this is my angle, I'm just going to do this, and then I'm going to go that way. But if I go that way, I'm just going to miss. So this problem says if this is 40 degrees, which I think that's fairly close. It's always good just to you know, draw a perpendicular to this. And then what I do, here's my technique. I always do, like, if this is a 90, I come in here and then just do a sweeping arc. And then the easiest thing to do is 30s. You know, divvy this up into 3 pieces. I think visually that can be very easy, especially with an arc. And then you can come back, easily put your 45 in. And then you can kind of do something tricky and be like, between 45, just do 2 more hashes. Each one of those is 5. So if I really want to say, hey, what is this line? Well, I think we're pretty close. They pretty much drew this about a 45-degree angle, so it would be just a little bit less. But hey, it's fairly drawn to scale. And then we could even see, like, hey, what was this angle? Well, if this was 45, this looks like this is 15. Maybe this looks like about 20 degrees. So at 20 degrees, like, hey, we come down here 500, and then we have to go along this. It doesn't say this has to be a particular magnitude. It actually just asks what that component is once we figure out this angle. And so, all right, so hell yeah. So that's kind of the general gist. I'm going to talk a little bit more about these members being in compression and tension. Alright, hell yeah. This is a fun game to play because we have this 400 over here, and all I get to do is go along this member and this member. And the way that it's set up is like, well, no, we're going to talk about this. Because this way I go this direction and then I go along that way. So can I even get to this point if I go along here and then I go parallel to that? Sure, I can go this direction and then over here. Cool. So now the game is just like move this point around and see if you can get to it. So I'm going to move this point, I don't know, up there. And so can I still have this in compression? You know what I mean? We're going to go down this. And then can I reach that point? Well, no, because I can go down this and then I can just go this way. So, you know, having having a force this way in compression along AC, I can't get to over there. So I have to maybe go this way. So if AC is in tension, I can have a tension member at AC, and then I can and then maybe go down this line. So I'm going to go this way and then parallel. And sometimes it's just nice to draw parallel lines. Oh, okay, hell yeah. So I could go this way and then that way to get there. And then once you find like one way to get there, just know that you could go another way. I could go this direction and then I could go parallel this way. So just draw parallel lines, and I could go this way and then that way. But I would still like first intuit, kind of like pick a direction you want to go and then see if you can go the other direction to get there instead of just kind of drawing a bunch of parallel lines. It helps your intuition. Okay, so in that case, this member AC was in tension, and then this member AB was in compression. I gotta put an arrow that way. Okay, so now the question is like, if AB has to be in tension, let's say we just make it a string, and then AC has to be in compression. I don't know what you would make, you know what I mean? I guess you could stack rocks like this that were just loosely connected with rubber bands. So the second you actually pull tension on it, it doesn't work no more. But that's visually sometimes useful to do. Okay, so if this one can only take compression, and I have to start at A, I can only go this direction. And this one I can only go in the tension direction. So I'm going to go this way just a little bit, and then I can go this direction. Okay, so I could get there with going in compression and then tension. So let's say I just don't go any in compression, and I could still get to there in tension. So just 0 to just no compression, and then in tension I could get there. So I could get here, here. So I could hit all of these points, and just a little bit of compression, a lot of tension. So heck yeah. So now I kind of have, I can get anywhere that way. So now let's try to come down here. So I'm going to go compression and then tension. Okay, for sure I can get down there. Now let's do a lot of compression, hardly any tension. Okay, I can get right there. So it looks like I can get any vector. I can have this force be directed anywhere along there. So let's put this force this direction and see what happens. I'm going to go in compression, and then I can't get there unless I put this one in compression, and it's a string. So sometimes visualizing that this is, you know, one of the things is a string really helps you out. So in that case, this model would not work. But if both of these are steel bars, hell yeah, you can get there. It just means that you're going to be in compression down this way. Well, are you going to be in compression on both of them? You're going to be in compression this way and then compression that way. Yeah, so if you're, and that makes sense. So sweet. And I think just by intuition, if I pull any direction in between these two, any vector direction this way and this way, these two members will be in compression. Cool. So because let's try to get to this point. You know what I mean? I got to be in compression down this part, and then I have to be in compression down that part. Or similarly, I'd be in compression. I'd be in compression down this part, and then I'd be in compression that way. So every point that you pick, you know, you can go two different ways, and it's a parallelogram. So let's choose one out here so you can kind of see that parallelogram. And then the other way to do it, is just draw parallel lines. So these are parallel. You can draw a bunch of lines, just make sure one goes through the point that you want, and then come this way. Sometimes it is useful to kind of draw more parallel lines, but then just make sure one goes through the point. So if I start here, I can be in compression, and then I would say this is in compression. So compression, compression, or compression, and then compression. Cool. So there you go. And then if I was over here, you know what I mean? What would I need to do? I would have to be in compression. Okay, so if this is a string, I said I could be anywhere. If this was a string and this was in compression, this is all good until here. So we're all good to here. But if this is a string and this can only take compression, are we good anywhere else? Let's see, because I have to have this in compression. No, I think that's it. If this has to be a string and this has to be in compression, I can just be here and here. But now what we're going to do is, hey, this can be in compression and tension. You know what I mean? So now we're just going to have just this as the string, but I can put this in tension. So I could go all the way up here as far as I want in tension, but could I go this direction? No, because that would be in the... I can't put this string in compression. But I could hit this point, right? I could go in tension, and then I could put this member in tension. So hell yeah. So now, if this is a string and this can both take compression and tension, I can go anywhere from here to there. And so there you go. So if this is a string, and the other member can take tension and compression, you're always going to have a scenario where it's 180. If I pull, and it's bizarre, because even if I just pull this way, it seems like, well, can't this take the tension? Sure, it can take the tension only in that direction. But we have a component this way, and that's just going to make this string go slack, and there's nothing to resist over here. So we actually don't have a statics problem anymore, because we have to deal with that component, that nothing is resisting that component. So, because this is a free pivot to move, I mean, I can put this in tension and compression, but I need something else to balance that. Alright, hell yeah. So now let's talk about the other two anomalies. If I turn this into kind of that chunk of rocks, stack rocks and then connect them with rubber bands, like this can only take compression. We just said that was all the way through here. This is the only slice. So it's not 180, it's actually just that slice between these 2 points. Sure, I can pull down on this. I mean, it's very similar to an arch bridge. You can see that. You can't pull up on a stacked arch bridge. You know what I mean? So let's say these are strings now, and that's as messy as we're gonna get. But yeah, and I got a new sheet of paper. You might as well just use this one. Okay, so I'm going to assume that these are just strings, loose strings. So now the last question is what direction? I mean, the first thing I would do is I would just draw these lines, you know what I mean? And could I get to here? You know what I mean? Hell yeah, I can go tension and then tension. So sweet. And then I can get to there, just tension along there. I can get any point along here. And so can I get to out here? No, because I'd have to go tension and then compression. You know what I mean? Or I would have to start in compression and then go to tension. So there's the parallelogram. So yes, if both these are strings, I'm really restricted to just pulling a force. But that's kind of cool. It's kind of cool that I could have these two lengths of string. They can't increase in length. But if I pull anywhere in this range, we're good to go. You know what I mean? I can't, and that should make sense. Like if this was upside down, and they're both strings, I think that's easier. Yes, like bring some gravity and be like, okay, if this is a string and this is a string, yeah, hell yeah, I would just visually be able to pull inside this window. If I put a bucket of water here, pretty heavy, and then just let go, it's no longer a statics problem. This is a pendulum, and this ain't doing nothing. So I think this was really useful to kind of go over like what's going on with some of these problems. So I think this was kind of part 1, and very useful. So part 2 is, I guess just a little foreshadow, is we're going to, and this one's tricky, because, just the fact that we set up parallelograms, this is one of those problems that kind of makes you, still use angles. Instead of just using the free body diagram approach and being like, hell yeah, these angles have components, I'm going to turn everything into components in the orthogonal, just the up and sideways directions. That leads you down like difficult trigonometry, where if you just draw this in, and then anywhere where you get a point, draw your horizontal, maybe draw a vertical, and then see if you can figure out maybe what some angles are. And then even just do what we just did, is just like, heck yeah. So we're going to draw this in, and then we're going to draw parallel lines to it, and we're going to go through this point C. And I guess we would need to use this sheet. And so, yeah, so let's do that. And that makes sense. We're going down this in compression, and then we're going parallel. So you can make the vectors. Just because this is the length, you can still say, hey, maybe this is 500. Cool. And then, that's very useful. If we are saying this is 500, 1, 2, 3, 4, 5, we've got to make this proportional, 1, 2, 3, 4, 4 chunks. So I'm going to say that's to 400. Cool. And then I'm going to draw these parallel lines in. Bummer. I thought I got that on the page good enough. But here we go. So now what do we know? I kind of use the Zorro method anytime, it just reminds me of, like, I don't know, Zorro. Even though no one watched that show. I don't know why. But anyway, so, and then we can find similar angles. Because if these are parallel lines, well, then the inside angles are the same. So I'm going to say, hey, this is 40. And in the problem statement, they were saying, hey, if this is 40 degrees, what's this angle where we can have a compressive force of 500 and pull on this at 400? So you know what I mean? If we have this bar, and then we have like a force meter down here, and I pull 400, this has to read 500. You know what I mean? And so so cool. So this vector is 500. This one is 400. And then we need to angle this to actually get the heck up there. So you can even just see, it's like, hey, that ain't the right angle. But now, like, what is this angle? So it's tricky. I would have not, if I kind of watched a person set this up, so I can't take any credit. But hey, here's another parallel line, here's another parallel line. So we kind of have this Zorro shape, and this is the same as that. Well, and I guess that's probably another identity that I do not know. If I have a straight line, and I have this line going into that with an angle of theta, alright, heck yeah. Then I have this same parallel line going into that same line, so heck yeah, this must be I'm going to throw that into my wheelhouse. I guess the other way to get, would be another way to get there. Whew. Yeah, I don't know. I guess it's the same thing. If I have two parallel lines here and here, and then I have two other parallel lines meeting them, then that these angles are the same. Cool. And then if these angles are the same, then we got that Z shape. And so we're good to go there. Cool. So this vector has to be 400. You know what I mean? So our thing isn't drawn right. Like this angle has to be like I have to shoot for that thing. which makes this angle bigger. You know what I mean? So this angle is too small the way it's drawn, and it's got to be much, much bigger. Alright, but now we're just set. We have this triangle drawn where we have this, we have 500, so it's super not drawn to scale, but 400, 500, angle of 40, and an angle we don't know, and then now we're just killing it with the sine theta. So what the law of sine says, is that if we have this side, so we're going to do 500, it's divided by sine of the angle. That ratio of this side divided by the sine of this angle is the same thing as this 400 divided by the sine of this angle 40. Cool. And then so we have to maybe get this sine theta upstairs, get this upstairs, so we're going to have 500 sine 40 is equal to, and let's get this downstairs, 400. That's going to be equal sine theta. And then we can just take the inverse sine of both sides, and that just makes theta. So hell yeah. So we have this, we can cancel out 100, so we're going to have inverse sine of 5/4 sine 40. Alright, hell yeah. So now kind of for a new, and then that's it. You know what I mean? If we want to throw it into our calculator, we got inverse sine 5/4 sine 40, and you can get on with life. It's 53.46 degrees. But one of the viewers is just like, hey, you know what I mean? It would be nice if we didn't have to rely on our calculator every time, and to get to something like this and actually, you know, be able to predict what the angle is. Because even here, we didn't do a very good job of predicting, and I can't say I did a very good job with this one of kind of predicting what the answer would be. But what we're going to do is we're going to do that part, and then I'm going to finish with how to not use your calculator with like sine 40 degrees. So it's useful to do things in centimeters. So this is 4 centimeters. I'm just going to say that's equivalent to 400. So now we get to choose. I guess let me pull out this one. All right, hell yeah. So we get to choose like this angle, and I mean basically that means that we get to choose this angle. I mean, if this is 0, this is going to be 40. And then, so this angle could be 40 to way out here, you know what I mean? So even just that is like, hey, this can be 0 to 90. Well, cool. Make it 0, you know what I mean? And I think that could be the first place that you try, is just like, well, I'm going to make this 0, and then so I'm going to have a 40 degrees, and we're just going to kind of use the guessing approach, you know what I mean? There's about 45. I'm just going to say there. So I'm going to go 5 centimeters, and then booyah. And then if this is 0, I got to go that way to get to that point, and I can't. I'm going to go 500 this way, and then I'm going to go along that member AB, and I just can't do that. So that was a horrible. Saying theta was 0 was really bad. And so yeah. But I mean, actually, my first guess was pretty sweet, because I was just like, well, if this is 400, I don't know. Let's just take the 500 straight down and then see what the problem asks. You know what I mean? So we took this 500 straight down. The problem says that this angle has to be 40. So sweet. I'm actually just going to visualize that. Here's one way: is just do this, do your 30s, do your 45s, and then hash that up twice, and you got. You know what I mean? This is 45, this is 40. So I'm just going to go just like that. And now what? Oh. Yeah. So this is the angle. Wait, what? Yeah. So if this is straight down, this angle has to be 40, and that's member AB. So this would be member AB. But we have to take kind of a parallel line from here. So let's just do that visually. From here, I'm going to go over to there. Hey, it looks like we get pretty darn close. Maybe we hit there by going parallel. So that was a really good guess. And like, there you go. So now we might be done with our guessing. If this is straight up and down, this is 40 degrees. Hey, what's our theta now? Our theta is 50 degrees. So, sweet, that seems like a pretty good approximation. We got 53.46, so there you go. I did this problem with graph paper, and I kind of really honed it down, and I wanted to know what side, you know what I mean, do I need to increase this angle a little bit more? Well, even from this, it's like we overshot. So sure, increase this angle, and then we're going to have a steeper trajectory. We're going to be going down 500, and then this angle steepens. And then we're going to have a steeper trajectory from there, and then we can hit that point. Alright, sweet. So now we're probably going to kind of end the video with the fact that our answer that we got for this triangle, this theta, let's write this in. So this theta was inverse sine of 5/4 sine 40. So this, how would we figure that out? Well, Let's talk about what sine 40 is. So let's draw a 40-degree triangle. And we're just going to do this just with kind of guesstimations. You know what I mean? Nothing too fancy, no graph paper. So I'm going to draw these. I'd say that's about a third. And then we're going to draw right in the middle, that's 45. Draw two more hashes. So one of these hashes is a 40-degree triangle. I don't know, just go out to there, who cares? And then drop it down. And now we have our perpendicular. So here's how, if I don't have a calculator, but I want to learn something about, and yeah, I'm going to say, hey, pretty confidently, that's about 40 degrees. Alright, so now I want to know something about this triangle, because, hey, what's the sine, what does sine 40 mean? Well, it means that if this triangle is like a unit triangle, if this is a dimension 1, or it doesn't even matter, this could even be the dimension, the hypotenuse, that the sine is related to this opposite. So if here's the angle, I just draw some sun shining rays, and it's shining on the sine component. I think that's probably one of the easiest things to do. Every time you get an angle, just draw some sun rays on it, and be like sun rays, sine. You know what I mean? Sun is shining on the sine. Booyah. Alright, so, but kind of two things are happening here. Is the sine component is a percentage of the hypotenuse. So sweet, if this hypotenuse, really big number, then this is just the percentage times that big number, and that is that dimension. Okay, hell yeah. So if this is 1, this is basically just like a fraction between 0 and 1, which is a percentage. You know what I mean? And so here's what I like to do, is either pretend, sometimes I like to pretend that this, what we'll be doing is pretending this hypotenuse is like has a length of 10. And so, and you don't need to, but for triangles that are really close to 45, it's visually difficult to, and I'll show you in a second. So what I like to do is just always come into the hypotenuse, and then first just take the hypotenuse, cut it in half. What this shows you is, like, visually you can see that length. And you know that length is 50%. Well, does this length look like 50% of the hypotenuse? No, this length looks much bigger. And we already know, you should at least know going in, that a 45-degree triangle is 0.707. There is some decimals that you should know. 30-degree triangle is 0.5, 0.866. 45-degree triangle. A 60-degree triangle, kind of same thing, just kind of inverted. And those three are the only ones you really need to know, but man, I mean, the next decimal is a 0 on this one. I think the same thing on that one, sine 45. There's a 1 right here, so it's to 3 decimals is just really close. Sine 60, heck yeah, this has got a 0 and then a 2. So this is just incredibly accurate. And as a decimal, this gives you more information knowing it this way than this is square root 3 over 2. This is 86.6% of what? Of the hypotenuse. Cool. All right, so let's get back to it. So we at least know that this number is going to be greater than 50% or 0.5. All right, so, but let's say we wanted to, you know, sine of 40, we wanted fairly accurate. So what I'm going to do is I just come in here and I'm going to do 1, 2, 3, 4. Now that's a harder, it's really easy to take a 90 and divvy it up 3 times. What's harder to do is take a length, let's say this is a length of 10, and then come in and put 4 hashes But I would get used to that. That's a really good skill. Come in and then, especially with a base 10 system, you can easily half it, but then you got to go divvy it up into 5 chunks, and that ain't no easy task. You know what I mean? I don't know if there's any other way to do that except just good practice. I messed that one up. You know what I mean? Because you can't come in at the halfway point. I guess you... I don't know any... Yeah, it'd be fascinating if I come up with other techniques. But if I got to divvy that up halfway, I don't know. I just kind of go for it and just visualize it. But that's pretty good. And in that process, you're getting good at making little hashes, even space. So that's where graph paper is king. But we don't want to do that. We just want to come in and be like 1, 2, 3, 4, 5. Okay, so I'm going to do the same thing here. And I'm just visualizing those hashes and try not to put too much emphasis. I want to be as accurate as possible, but you know what I mean? At the end of the day, you can only be so good. Okay, so hell yeah. Now I'm going to count them up. 1, 2, 3, 4, 5, 6, 7, 8. So I got 0.8, or I got 8 here. And then if this is 10, I got 8. 1, 2, 3, 4, 5, 6, 7. And I got 7. I probably overestimated, because what I do know is that if this is 40 degrees, this has to be less than, so I'm going to try it one more time. Alright, so here's the 40 coming in, and then we're going to divvy this up. 1, 2, 3, 4, and we're going to go 1, 2, 3, 4, 5, 6. There we go. 1, 2, 3, 4, 5, 6, 7. I think this is about 0.75 and this is 0.65. I don't know. You know what I mean? So there you go. I think this is between 0.75 and 0.8, and I thought this was 0.65 to 0.7. But I know this has to be less than 0.7 just by a little bit. Okay, sweet. So there's one way to estimate, sine 40. And this is the sine component, so I'm just going to say it's 0.65. But now this we have to multiply by 5/4. Like, what is that? 5/4 is 4/4 plus 1/4. I would definitely do that because I can easily see that's 1.25. So I'm going to multiply 1.25 times this. How would I do that just from a guesstimation process? Well, I got one of them, 0.65, and then I got a quarter. Well, let's do half first. What's half of this? That's about 0.3. What's a quarter of that? About 0.15. Cool. So let's add this up, and I got 0.8. Okay, so hell yeah. So now I see that this says inverse sine of 0.8. Now let's talk about what that is, because that's anytime you're doing an inverse sine, always make this a ratio. So now we have 0.8 divided by 1. We're going to draw our triangle. So our triangle is going to have a hypotenuse of 1, and then it's going to have a sine component of, if this is 1, this has to be 0.8. So if I go 1, 2, 3, 4, then I have to go 5, 10, maybe 8 right there. So this has to be the sine component, and then this has to be a perpendicular. So there you go. So now I have this being 8. 1, 2, 3, 4, 5, 6, 7, 8. This being 10. And now I can figure out maybe what the angle of this is, just from that perspective. Not the best, but I mean, it's at least something. I'm going to divvy this up 3 times. So there you go. I know this angle is less than 60. And let's use my method. Draw the 45 and then draw the 2 hash mark. I'm going to draw a hash mark right there. So yeah, I think this is about 50. It's going to be 50, but just greater than 50. So I think the angle right there is 51. 51, I would guess pretty close to, this is 55, this is 50. I mean, I got to guess 51 just based on my drawing. So we do have an error because the actual answer is 53.46. But you know what I mean? Even right here we guesstimated, and but yeah, that's just one method to guesstimate an angle. And I just think that's useful. I'm like, how is that not useful? If you don't have a calculator and you're staring at sine 40, and then you got to multiply by 5/4, and then you got to take an inverse sine, it's just like, holy Toledo. Yeah, you got to do a lot of it'd be very difficult to do by hand. All right, the other method, since we're playing around with this one, I gotta throw in a new battery. All right, hell yeah. So you know what I mean, we didn't have to go down that route for sine. Well, no, I think we had to for sine 40. Yeah, that's fast. I was just gonna go down the route of being like, well, couldn't we do a linear approximation? But I would really only use linear approximations consistently between 30 degrees to 0 degrees. Hell yeah. Like, let's say this was sine 20 5/4, and then let's do the inverse sine of that first before we do anything else. Because if I have this as sine 20, you know what I mean, can't I just get the decimal? Because if this is sine 30, heck yeah, I know that's 0.5. But what I do know is that it's linear. Sine of 0 is 0. And sine of 15 is half of this, is 0.25. And it's close enough. It's an approximation. And so I think linear approximations can be difficult, but I think you should do them like you would do, like, hey, velocity. Like, let's say, this is how I do it. You know, if I have, let's say you have 60 miles per hour, and then you have 2 hours. And then you want to know the distance. Like, what do you do to these? You know, this is miles per hour, and this is hours. Like, what do you do to these two units to get what you want? Distance is in miles, and that's what I want. So I just multiply these two things together. Cool. So same thing here. I've got 30 DEG degrees, and then I have, and then I have a ratio of 0.5. That's the trickiest thing, is there's no units on this. It's just a ratio. I'm just going to do RAT. That is the ratio. Okay. And well, this, yeah, let's see what we're doing. And I want to know what sine of 20 is. So then I have 20. So these are equal, I guess. And man, yeah, I guess I just have to set these equal. So just as if you have 60 miles per hour, you're equivocating two things that aren't related, really. You know what I mean? You're saying that, hey, so this stacks. So you can say, hey, 60 miles is equivalent to 1 hour. You know what I mean? It's and they are related. It means that if you're driving this speed, you get to go 60 of these in the time of 1 hour. So yeah, it's just kind of fascinating how factor label. I'd never like it this way, because usually it's bizarre how one thing equals something else that's like not related. But this is the sine of 60 degrees, which already is the ratio, but I guess we're equivocating. So the same thing here, we're equivocating two things that aren't related. I'm equivocating 30 degrees in a ratio of 0.5, and so that becomes this. So we have 30 degrees is 0.5 ratio, and like, let's say we struck out and I said 60 miles per hour, and I said 120 miles. Well, now I have 60 miles per hour, and I have 120 miles. What do I do to this to get the time in hours? You know what I mean? That's what I want. Well, hours is down here. So this thing doesn't really represent, you know, what I need. And so, so you know what I mean? Like, I can't multiply these. That would be miles squared divided by hours. So, you know what I mean? You kind of have to figure it out, but we're gonna take this divided by that. The miles will cancel and the hours will pop upstairs. So that's going to be 120 miles divided by 60 miles per hour. And I like doing things with speed, because we're all used to, like, especially miles, well, maybe meters per kilometers per hour, depending on if you're in a different country. But yeah, miles per hour, just speed. We're just used to speed. All right, so we're going to do the same thing here. we're going to have this ratio, but we're just going to, let's just write it the other, like you would say 60 miles per hour. You would never write this the other way, though. You'd never say 1 hour per 60 miles, but you can. Both are very useful, because had you have done this, then you could say, yeah, and I have a distance of 120 miles. Now I can just easily multiply these two, and then I can have an hour, 2 hours. Cool. So we're going to do the same thing here. It's kind of just linear approximation. So if I have this, I also have the ratio 0.5 ratio divided by 30 degrees. And so let's bust out. Yeah, and so I want to know what sine of 20 is. So sine of 20 is so I'm going to take that to 20 degrees, and I want to figure out what the ratio is. You know what I mean? Because sine of 20 gives me the ratio. I want to end with the ratio. So I'm going to say 20 degrees. Well, I do know that 30 degrees is a 0.5 ratio. Cool. So degrees cancel, and I got 2/3 of 0.5. That's 2/3 of a half. That's going to be 1/3. Sweet. So that was actually difficult for me to see, that sine of 20, and it shouldn't have been, because if I have sine of 30, and I go to sine of 20, and then go sine of 10, and then go sine of 0, well, if whatever, sine of 30, whatever number it is, sine of 20 has to be 2/3 that, sine of 10 has to be 1/3 that. So now I'm kind of learning, you know what I mean, going through this stuff. So cool. Let's set this up again. So we have inverse sine 5/4. I want to know sine of 20. This is what we're interested in. So I just said that sine of 20, we had, I know what, so I'm going to take that 20 degrees and say that 30 degrees is equivalent to 0.5. That's the ratio. And so we're going to have 20 divided by 30. That's going to be 2 divided by 3 multiplied by 1/2. And we're going to get a ratio of 0.33. So sweet. So this right here is a ratio of 0.33, or 1/3. We're going to do 5/4 multiplied by 1/3. So that's going to be 5/12. Even just right here, how do we approximate this? I could say, hey, close enough to 5/10, get on with life. That's 0.5. And then that's pretty good. But now that the denominator is bigger, what does that do to this number? That makes it smaller. 5/12 is smaller than 0.5, and so I have to kind of take that into consideration. So I just know it's smaller, so it's going to be 0.4 something. But I'm going to go over like what I would do. So I would the next step, I've been just trying to figure out ways to not use your calculator, because if this bottom is like a function of 100, and then I can multiply this bottom by something to get it to be 100. Then whatever the top is, that just becomes that number, and I can move the decimal place too, and I can get a percentage. So let's do that. So like 12, so I'm just going to start with 12 times 10. That's 120. That's way too much. But let's subtract a 12, and you know what I mean? Well, yeah, let's do that. You know, that's going to be 108. So cool. And then we need to subtract one more. So that'd be 11, but we need to subtract one more. But then we get to kind of 96. So this is 8 points away. This is 4 points away. So then like, hey, so I need if I subtract 10, that's too much. I need to multiply 10 and maybe a third. So 10.3. So 10 and a third. So there you go. So even just right here, we're doing better than linear approximation. We're doing better than just guesstimating. But I kind of just do this stuff for fun. But sometimes it's just like, hey, we just got on with life. It's close to 0.5. And then never lose like the forest for the trees. What the hell? You know, we were saying, hey, we were taking sine of 20, which we thought was 0.33. And then we have to multiply it by 5/4. And then we get 0.5. And then we're going to take the inverse sine. So what's the forest again? Well, we have an angle with a hypotenuse of 1 and a sine component of a half. Okay, so that sounds like a 30-degree triangle. So this sounds about like 30 degrees. Cool. So 5/4 sine 20, pretty darn close to 30. Is it going to be? But we know this is going to be a little bit less. It's going to be like 0.45 maybe. So that makes this maybe like a 25, 27 degree. So that's kind of where we're shooting, and cool. And then we also, yeah, so we're good there. Yeah, I guess I was just going to say we can use linear approximation. If a 30-degree triangle is related to 0.5, the opposite is true. If I do end up saying this is 0.45, this is the ratio. So I'm going to say a 0.5 ratio multiplied by 30 degrees is the degrees. You know what I mean? So this is so cool, turning linear approximation into something like, you know, speed, like miles per hour. All right, hell yeah. So if we did do this, we would have, well, I don't know. I'm just going to throw it in my calculator. I'm not supposed to do that, but 0.45 divided by 0.5. Oh, I see. I could have done that. Bummer. I hate when I do stuff, but no, it's good. Because if I see 0.5 down here, well, can I just multiply by 2? Hell yeah. And then the denominator becomes 1. No duh. And then this is just 0.9 times 30. So sweet. 9 times 3 is 27. And so we're going to have 0.45. Yeah, almost a ratio of 1, a little bit less. So we get 27 degrees. So yeah, I was just using my knowledge about maybe what a 0.45 triangle is. You know, and it's just, you should kind of tabulate this in your brain, but you'll probably, from a pure memorization perspective, you're probably going to kind of forget that. But heck yeah, definitely the fact that linear approximation works really good from triangles from 30 degrees to 0 degrees is just really handy. Okay, so yeah, we were really close on this because we had this ratio of 10 and a third, I thought. You know what I mean? If we multiply 12 by oh no, we messed that up. So so 12 times 10 is 120. We have to subtract 1, that's 9. So I don't know what the hell I was talking about. So this would be 9 times 12 is 108. 8 times 12 is 96. So this is undershot, not too undershot. So we just need 8 and a third. So we're going to take 8 and a third multiplied by, what are we multiplying? By 5. Because if we take 8 and a third by 5, the bottom we're assuming is pretty darn close to 100. So we have 8 times 5 is 40 divided by 3. I guess we're kind of in the same predicament. Is what's 40 thirds? Yeah, I guess that wasn't the smartest. So let's just do, yeah, the easier way to do this, the linear approximation way, because we're already down to just kind of guessing. 8 times 5 is 40, but then 9 times 5 is 45. But we need 1/3. We need kind of 1/3. You know what I mean? So instead of 40, 45, this is 5 point different. We're gonna have like I don't know, probably like 42ish, 41.5. There you go. So oh yeah, and then what the hell were we even trying to find? This was 41.5 divided by 100, so we got 0.415. So there's a chance. Let's see if I even did this right. So 0.415 was our triangle. And so if we come down here to 0.415, that's our ratio. 0.5 ratio to 30. And let's do this. So we got 0.415 divided by 0.5. But we didn't yet. Damn it. We don't need to do that. We could double this. So that's 0.82. That's 0.83 times 30. That's close to 0.8. Times 3, that's 24. And so, sweet. So we think our angle is closer to 24 to 27. So let's find out. Let's see how much craziness we did, and let's see if we got anything right. So we're going to do inverse sine 5/4 sine 20. And please be closer to, what did we even say? 24 degrees than 27. And sweet, it's 25.31. And so, hell yeah. And if we got this 0.415 divided by 0.5 times 30. And, well, that was, yeah. So our guess was 24.9. So if we actually, for what we did, we were pretty damn close. So this linear approximation is pretty slick. It's just difficult. Like, what did we even do? We said sine of 20 was going to be 1/3 of, well, no, it was going to be 2/3 of the ratio of 0.5. So we had 2/3 of a half, which is 1/3. So sweet. And then we took 1/3 times 5/4 and got this ratio 5/12, which sucked. So we needed to turn this into 100, and then that really gets us really close. And because we did 8/3, you know what I mean? We could have just said 8. 8 times 5 was 40, but 9 times 5 is 45. But we saw that it was closer to about 8 1/3, so we chose 40, what did we choose? 41.5? And, you know what I mean? Let's choose 42, just for the heck of it. If we chose 42, that's going to be a ratio of 0.42. So this was inverse sine of 0.42, and then we took that 0.42, divided it by the ratio times 30. So 0.42 divided by 0.5 times 30 was 25.2. So that's my approximation for that. So anyway, and I think it's difficult to do approximations because they're approximate. There's no satisfaction in getting a right answer. So it's like why spend a lot of time like trying to get an approximation, because it can be a lot of work. Where, you know what I mean, if I got miles per hour and distance, man, you're just going to chisel out like an actual number, you know what I mean? But yeah, just kind of relying on this idea that, hey, the ratio from 30-degree triangles to 0-degree are linear from that 0.5 ratio down to a ratio of 0. And, yeah, so that's kind of what we used. Yeah, that's it. That's exactly what we used. And then we get, the hardest thing was to get this decimal as a ratio. But once we did, then we were able to, and I guess the interesting thing is we didn't, let's do this one more time. Because I don't even think we needed to, I don't think we needed to spend too much time getting as a decimal. I don't know if this is going to pay off, but this is going to be the last thing I'm going to do before this video, so let's do it. Alright, hell yeah. So we have the angle, inverse sine, 5/4 sine 20. We want to approximate it. So let's do it. So what's inside there, so we need to take the inverse sine. We have this 5/4. We said this is going to be 20 times 30 divided by the ratio of 0.5. So this is, it's good to throw this in. Ratio, this is degrees, hell yeah. So we still have the ratio. Alright, so now we have this, which is, you know, what can we cancel? We could probably factor out, this could go to 10, this could go to 5, and that goes away. So now we have 5, 5, 5, and then 30, but this is going to be 5 times 6, so one of those goes away. So we got 25/6 as our ratio. Okay, but if that's our ratio, how do we get degrees? Well, we just said we take the ratio is going to be 0.5 to 30. You know what I mean? So I don't know why I chose to go back to degrees, but it is useful to remember what decimal triangles are. So there you go. So this and then this is degrees. So this ratio cancels, and then we get degrees. And this is 1/2. The 2 pops upstairs. So we have 25 times 2 times 30. I'm going to 6 goes. 30 is 5 times 6. So I'm going to cancel out a 6 right there. And we've got 25 times 2 times 5. Oh, I think I did something horribly wrong. What did I do wrong? All right, let's do that one more time because that seemed pretty useful. So we have this, and it's just, yeah, we have this as our ratio. So we have 5/4, and we have 20 degrees. We're going to take 20, divide by 30 degrees, and that's representative of 0.5. Oh, that's where. This is 0.5. So this is 1 divided by 2. So there you go. And then once we... so, yeah, what does that give us? That gives us that ratio. Now we're going to multiply it by 5/4. So this is, let's simplify this. This is 5, 2, 4, 3, 2. Okay, but this is our ratio, so at some point we need to take that ratio, and we're going to, we have 1/2 down here as our ratio, and then we have to multiply it by 30 degrees again. And so this is the same thing as 2 upstairs. So the 2 cancels, the 3, this becomes 10. I'm going to go 5, this becomes 2. 2's cancel, and we get 25. So straight up, yeah, that's really fascinating. I'm sure you could get there a lot faster. But, so, yeah, that's really bizarre. Let's do it all in one go. So the angle here is 5/4 is a ratio. We got to take this 20 degrees, divide it by 30, and then we'll have a half up here, which is just multiplying by 2 again. So we have that. This is our ratio, so then we have to say the ratio is 1/2. That's going to be upstairs, and then downstairs is going to be that 30. Oh, I feel like I messed up. Bummer. We were really close. I messed that up. So we have 5/4 is our ratio, and then this has to be a ratio. So to get 20 degrees as the ratio, what's sine of 20? Is 20 divided by 30. And then we have a 0.5 up top, which is 1/2. So that looks good. And then once we have, this is the ratio, we have to multiply that by 1/2, and then oh yeah, divide by 30. Oh, what the hell? Yeah, maybe that'll work. Maybe it'll work. I don't know. Let's talk through it one more time, and I might just write it again. So we have 5/4. We're going to take this degree, make it a ratio. That's going to be 20 times 30 degrees, and I'm just going to do 0.5. Keep this ratio just nice and tight. Then this is our ratio that we need to convert. So the ratio, oh, we got to put the ratio 0.5 downstairs. That was the deal. I got to divide by. So this has to be 2 divide, 0.5 downstairs, 30 upstairs. So it's got to be a 2 and a 30 upstairs. Yeah, so holy hell. So that just cancels. So yeah, I'm sure there's a real, holy Toledo. So I did not see that. Inverse sine of 5/4 sine 20 is just 5/4 times 20 degrees. Oh, see, I'm probably an idiot, like that I didn't see that. So anyway, so we have 5 times 5. I mean, this is 5 times 4 divided by 4, and then we get 25. So wow, so that was an aha moment. I'll even have to take a look at like what, you know what I mean? Because I don't think this works. That here, let's do this. Like, I don't think there's an associative, or I don't know the different properties, but I'm sure inverse sine of 5/4 sine 20 is going to be, you know, this is just a linear approximation, so it just happens to be that way, just because it's a linear approximation. But if we take inverse sine 5/4 sine 20, this is not the same as taking this 5/4, because yeah, if we have inverse sine of sine 20, you know, inverse sine is saying like, hey, this triangle of 20 degrees has a ratio over here. that ratio, if I have a triangle with this ratio, hey, what's the angle? That's what the inverse sine says. Well, that's just one and the same. You're doing so those operations just kind of nullify, and obviously we're talking about a 20-degree triangle. But the opposite is not true. If you do 5/4 in here, so if I do 5/4 outside of the inverse sine, and then do sine 20, these two numbers are not the same. But it gets me the approximation, hell yeah. So that is really cool. But see how this actually is 25.3 degrees, but the approximation is just 25. So I'm glad I went through that hellscape just to get to like something that was just like, ooh, that is cool. If I have an angle that's 30 degrees to 0, and I have this inverse sine of a ratio times sine, I can just bring this ratio outside. So this is just going to be 5/4, and obviously inverse sine of sine is just the degrees, and I have and now I can do this magic. 20 factors to 5 times 4 divided by 4. 4's cancel, and I get 25. Alright, hell yeah. So we're done with this one. This one's pretty good. I don't know how to make these into shorter videos, but we're just doing long format. I think as I get... See, I just love working through this stuff because you get to see it real time. You know what I mean? You're going to be sitting there just scratching your head. And, yeah, it's just kind of fascinating. Yeah, to follow the math and to realize, because I've had that come up before. It's just like, well, no, you can't. You'll get something like this, and you can't take that outside. But now I know that I can. It's just going to be an approximation, so that's kind of cool. All right, I think I'm done with this one. Thanks for joining me, and that's a video.